on to session 2. So now we're going to continue where we left off on the ammonia testing. Ammonia testing is something that will be so much easier on the photospectrometer because you're getting a nice colorimetric reading, bright color to let you know if you have a high intensity of ammonia. So we're just going to focus on some of the things that will affect your sampling. The distillation test that is mentioned in the slide over here, I'm not going to go over that because too many people don't use the Nestler system anymore. So it wouldn't be an effective use of our time. So we'll go over what you're looking at for a high concentration of ammonia. The distillation and the titration method is preferred if you really have a high concentration of ammonia. And then you'll look into your standard meth for that type of book. But for the most part, you're going to be looking at your colorimetric ones, and that's a smaller load loading. For the plant application of ammonia, for ammonia, when it's present, it's going to mean in your chlorine system in a wastewater plant that you have some nutrients there. And the nutrients, the ammonia is going to create chloramines. And that's the same with the water treatment plants. Water treatment, you like to see the chloramines, the mono, the di, the trichloramines. You're looking for that in some areas. Whereas the wastewater facility, if you get ammonia into your contact chamber, it's going to steal away your chlorine for your actual demand. It's going to give you extra demand. The presence of the chloramines, that has a combined residual, meaning you have free chlorine and total chlorine available on that. And we'll go over a lot of that more in the chlorine section. High ammonia in the treatment for a wastewater facility means that you have very poor while you're upward condition as far as your air bay, and your secondary treatment is very poor leading into your contact chamber. So things upstream are poor if you have high ammonia content leading in there. Moving into nitrites, 1 nitrates, nitrogen, 2 parts oxygen. That's your nitrites. You're going to find that in your standard method, part 4500. It's very short-lived form of nitrogen. However, it's toxic to aquatic life in humans over 1.0 milligrams per liter. In raw sewage, you're going to see below 1 milligrams per liter of nitrites because of it being such a short form. And in your advanced waste treatment plant, you're going to want to treat that nitrite to below 0.2 milligrams per liter. Nitrites is tricky once it gets into a chlorine contact chamber because it consumes up to 5 times its weight in chlorine. So that means for every part of nitrite in the chlorine contact system, it's going to take 5 parts of chlorine just to consume it. So that's about 41.7 pounds of chlorine it's going to take to consume that 1 parts of nitrite at 1 mgd. So it's just very wasteful of the chlorine. So take care of that nitrite in the ammonia and nitrification stage in the air bay, as opposed to letting it go out to the contact chamber. When you're doing a nitrites, check for your pH and alkalinity of the sample, so that if it doesn't exceed 10 on the pH and alkalinity of 600 milligrams per liter, because that's going to affect your sample. Because at that time, since it's a short-lived organism, it has enough alkalinity and pH for it to do any kind of work. Nitrates, nitrates, you'll find that in the standard meth, part 4500. NO3, so now it's an advanced form of the nitrogen cycle. It's used for fertilizer, stimulates growth in plant and algae, and that's why there's that numeric nutrient criteria, because stimulating growth in algae in a waterway would reduce the water quality level. The nitrogen and the TKN, which is the total ketol nitrogen, that is a measurement that they use for the combination of the ammonia and the organic nitrogen, and that reading is what a lot of wastewater plants use, is the TKN. Now, raw sewage should be 20 to 40 milligrams per liter, and that depends on your on who is discharging to you. So if you have a fertilizer facility that's discharging to you some sort of processed water, then that might be a higher number. Or if there's some pet food on your line, it may be a higher number. You also have higher carbonaceous activity and chemical oxygen demand, so you're going to have more issues than just the nitrates. Let's see. Your effluent should be definitely less than 20. Your secondary effluent, and for that's leaving your secondary clarifier. And for most plants that have reuse water, they have to discharge less than 8 milligrams per liter when they're discharging into some sort of reclamation field, or some irrigation medians, golf course, whatever your irrigation source is. For the most part, it has to be below an 8 milligrams per liter if you're permitted for that. Let's move on. For your nitrates, your collection location, you're not going to see. Let's get back a slide real quick. Your TKN in the raw, that's your ammonia and your organic content, not your nitrate content. So it doesn't confuse you on this slide, where your incoming influent raw sewage shouldn't have nitrate in it. But your secondary effluent, since you're going to have the activity of the aeration basin from the raw to the clarifier, the secondary clarifier, that's where you're going to get your nitrates because of the nitrification cycle. And that secondary effluent, leaving that clarifier, should be below 20 milligrams per liter. And without denitrification, an advanced waste treatment program would have 20 to 40 milligrams per liter, but the same AWT plant, but after denitrification, can go up to go below 1 part per million. Here's a nice little layout of a wastewater facility. The water facilities, they do have the same primary treatment where they're screening out any big debris. Then they'll have a clarification for settling and flocculation tanks, and then they'll have some sort of filtration system to remove any of the big, or I should say the smaller total suspended solids, and then disinfection for chlorine. Some places use ozone, some places use UV, but that's mostly your disinfection side. Nitrate test. For the most part, you're using either electrode method or a colorimetric analyzer. Nitrates or nitrites, they have electrodes that are sensitive to nitrates and nitrites, and that's where you're going to get your reading from a meter like that. And the method is preferred if the nitrate has a very turbid sample or excess color. That's when you're going to want to use some sort of sensor as opposed to a colorimetric way of sampling. If you have very low TSS and low turbidity, then a colorimetric might be a good way to use to sample nitrite or a nitrate sample. Well, leaving that portion, we're going to go into acidity, alkalinity, and pH next. So acidity of the water is basically the measure of the quantitative capacity to react with a strong base to a specific endpoint pH of 8.5. That's your textbook definition of acidity. And you can also find that in your California Manual, the Volume 2. The capacity of the water or wastewater to neutralize acid is your alkalinity. We briefly mentioned that before. And a measure of how alkalinity is also a measure of how much acid to liquid it takes to reach the endpoint pH of 4.5. This is a alkalinity test that's using the methyl purple. So A is the methyl purple itself. You'll see on the slide A. B is the sample supernate. So that means you're taking this sample from a mixed liquor. You're letting the mixed liquor settle out and have some sort of supernate on top. And you siphon off the supernate, and that's where you get that clear sample of B. Then you add 6 drops of methyl purple. And the methyl purple is actually green when you're adding it to the sample, but you titrate it with with sodium hydroxide. So once you drip that sodium hydroxide into that green methyl purple sample, once you see the color purple, then that's where you're going to say your endpoint pH is. You stop dripping in your acid, your sodium hydroxide, before you, and then that's how you get your reading. And they'll tell you X amount of sodium hydroxide it took for this methyl purple to turn from green to purple, and that's where you get your alkalinity, whatever that X number is. Here's what you would need to do the same titration using a sulfuric acid basis, and you have a Emerson Erlenmeyer flask with a mechanical stirrer that you put in there to. You don't want to whip it around in there. You want it to stir uniformly and at a nice pace. And then you're going to do the same thing. You're going to drip into the sample, the sulfuric acid, until you get to an endpoint of 4.5. So here's a picture of the mixed liquor, and that's over here on your left. That's a digester sample from a advanced waste treatment plant digester, and you're monitoring their pH here on this side, and the sulfuric acid is getting dripped in. So the pH to start was 6.0, and your endpoint is 451, and it took 311 milligrams per liter of the sulfuric acid in order to get to that endpoint pH. And so that's the burette here is 100 milliliters. So imagine doing this 3 times, and then another extra 10 in order to get this endpoint pH. This form alkalinity test is especially important for monitoring a digester health, because you don't want your digester to be too much alkalinity where it's going to have a lot of activity, and that activity now could actually eat away at the lime in your structure, your tank. So you need to balance off that pH, add some sort of a basic, usually it's calcium, when you just put in a lime slurry in your air bay, and that's going to keep that temperature up. Your pH is the balance of hydrogen ions to hydroxide ions. So just think of it as a scale. If the power of the hydrogen is high, then that's where you're getting your basic versus your acid. once it tips the scale one way or the other. So 0 pH means you're going to have a very acidic, it's strongly acid, whereas 14 pH is your base, your strong base. 7 is neutral, and that's what you're going to find in pure water. Most wastewater is going to start around pure water. If you have too low of the acid content coming in from an industrial source, it may be as low as 6.2, but you're not going to see raw pH below 6.0 unless there's a significant industrial source. Okay, I'm going to skip over to your tools for pH. The pocket meter to your left will give you an instantaneous reading. Then you have some strips. The pH strip that's red is giving you a base, so once you stick that in the sample, it'll kind of give you a color, and that color would be more of a blue hue, depending on the concentration of the base. And then you measure that to a scale somewhere, a color scale, and that might be on the box or on a separate pull-out sheet, and you read the amount of, you've matched the color to give you the amount of pH, the base level or the acid level. This next picture is showing you the buffer solutions again and a pH probe. The pH probes, however, work in conjunction with temperature. Your pH is definitely needs to be have some sort of temperature compensation in order for it to work. Your raw wastewater is going to be about 6.8 to 8.0, and that even counts for raw water sources. Undigested sludge 5.6 to 7.0. The digested sludge is going to be closer to water. And the effluent, plant effluent, should also be closer to water. If it's 7.8, you've got a lot of additives in there, something that caused your pH to spike high. The pH calibration, this is showing you how to calibrate your pH, and that's just using little small beakers, and you see the 7 in the middle and the 10 and 4 on either side of it, and it's showing you that the 7 is automatically temperature compensated. That's what ATC means, and it's in Celsius, and you have the pH saying it's ready, it's calibrated, and that measurement is 7.0. We'll move over to turbidity, and touched on turbidity earlier, but turbidity is the optical property of a water sample that causes light to be scattered and absorbed rather than transmitted in a straight line through the sample. So if you were to imagine a light source on one side of a meter, and there's a sender and a receiver, between the sender and the receiver, if you have clear water in a vial and you put it in there, it flows straight through one side to the next. But imagine there's some particles in that water, that light's going to be dispersed or scattered, and the refraction of that light being scattered in that vial from one side to the next is where you get your turbidity reading. So that's where you actually have, if it's a great amount of scatter, that means it's a high turbidity sample. And if it's hardly any scatter, low particles in the water, that's a low turbidity reading. So nephelometric turbidity units is one of the ways they measure turbidity, and that's an NTU. That's the most popular way that they measure turbidity. But there's others. There's a Jackson turbidity unit and a formazine turbidity unit, and the formazine, the FTU, is what they use to calibrate the standards, and that's usually it's nice dark color, and they'll do even up to 2,000 sometimes on the turbidity calibration. So here's a blank. If you remember blank, a blank is just DI water, it's not sample water. Then 20 means that one vial has a formazine, a FTU of 20 milligram, or excuse me, a 20 refraction of the water. So that's what it's going to be in FTU units. And then the 100 is saying it should read 100 on your turbidity scale. And so that's formazines put into it. So that's what's making that NTU standard. And here's your meters that you get, a bench meter, and you got a sample cell. So your sample goes in there. That's how you get everything. It's very simple. It's a simple test. Now we'll scoot over to the chlorine. Chlorine's a little bit more difficult because there's a lot of things that address the chlorine side. So with the chlorine, it's a green yellow gas, dissolves easily in water. It's used for disinfection and sanitation. Remember that chlorine is heavier than air, so if there's a gas chlorine leak, it's going to sink down to the bottom as opposed to go up higher. The atomic number for chlorine is 17, so if you see any truck that has 2017 on it, it's going to be a truck carrying chlorine. And the atomic mass is 35.4, making that heavier than air. Liquid chlorine is 5 times heavier than water. So that's another thing you remember. Aqueous solution, they're very corrosive. So if you have high chlorine in your system and it's going to go through any tank that has metal, it's going to be corrosive to that tank. Some of your terms for chlorine: total chlorine, which is a combination of chloramines and chloro-organic compounds found in effluent disinfection processes. That's everything. Free chlorine is continued oxidation of all that combined residual, and free chlorine is where you get that off-gassing. You smell the chlorine. That's more chlorine that could be saturated in the water, so it releases now, and that's where you get a breakout of chlorine. You'll have to know chlorine dose, which is the supply or feed of chlorine to a process, and the demand is the amount of chlorine needed to oxidize organic matter in the chlorine contact chamber, CCC, to produce a chlorine residual. So the chlorine demand is your doses, chlorine dose minus your residual. That gives you your chlorine demand. Total chlorine residual is all your combined forms of chlorine plus free chlorine, whatever that chlorine is that's getting out of the aqueous solution. Chloramines we did go over. That's basically your chlorine plus your ammonia. That's where you get your chloramines. Here's a simple breakdown of what's called a breakpoint chlorination curve. On your left, you see the chlorine residual going up, and on the bottom, you see the dosage go up. So the first thought is, if you have your chlorine residual going down, then you need to just turn up your chlorine dosage and everything will be fine. Just turn up your chlorine. But it can actually be counterproductive. And this breakpoint chlorination curve shows that. It shows that your initial chlorine demand, when it's not met, then you need to increase your chlorine dosage. And then you start oxidizing your combined chlorine and your chloramines once you increase your dosage to a certain point. And once you start oxidizing your chloramines now, that's where your chlorine dose curve starts falling back down. So once that dose curve starts falling back down, you're going to need to decrease the chlorine if you don't want to get the free chlorine, so that you can go right back up the curve. So if you're looking at a chart for a wastewater plant that needs to chlorinate, you start turning up the chlorine, and you'll see all of a sudden the chlorine will drop back off, the residual. That means you've hit that point where you're oxidizing the chloramines, and you need to back off of the chlorine feed before you hit breakpoint. But let's say you're a water treatment plant and you want to have breakpoint chlorine, you would just keep cranking up the dosage till it passed the oxidation point of the chloramines, when there's no mono, no di, no trichloramines left, and then you hit your point of breakpoint. And that's where the off-gassing starts, and you're going to have, for it's a 1-to-1 ratio. For every part of chlorine dosage you add, it's going to give you 1 part of free chlorine in a 1-to-1 ratio. And it makes kind of easier for a water treatment plant to make sure they have proper chlorine dosage if they just operate under breakpoint chlorine. There's a few methods for analyzing chlorine. We're going to basically go over the last 3 methods. The iodine method, don't really use that much. But here's me many moons ago when I was a wastewater operator at a facility. So I'm taking this sample and I'm showing you how it's done. Got my PPE for the sample, which is personal protective equipment. And showing the chlorine is collected from the field, processed in the lab first, before the chlorine starts dissipating. Filling 2 sample vials at the same time with the field sample. One is going to be my blank, and the other one is going to be my actual sample that I use. Looking at the meniscus line, of course, you'll be holding it closer to your eye as opposed to showing you down here. But in order for me to take the picture while I was showing you the meniscus line, I had to put it down. But when you're checking for the meniscus line, you want it eye level to where you are, and you're looking at that vial to get that bottom curve in the water sample. It's important to dilute sample with deionized water in equal parts if the field sample is out of the max range of your sample kit. This kit is a kit that I believe goes up to 20 milligrams per liter. So if I were to add a reagent to the sample and it went bright purple, then I know it's far out of the range of this meter. And then what I would have to do then is add some deionized water, DI water, to the sample and make sure I know how much, so I can do that calculation to figure out, okay, if my reading is 2, but it's only half of a sample and half DI water, then my actual chlorine residual is 4 parts per million and not 2. So that's what I mean by deionizing and doing a dilution. This is showing my 0. So you can see on the slide on the left, it's showing a 0, and then the slide on the right is my actual residual. And the residual for this meter, you have to push the input that says read sample, and once you read the sample, it gives you what it is. So this one is saying it was a 1.47 sample that red color was giving me there, that pink color. And that's the chlorine. That's what it means. That's how you implement it in your system. So now we're going to scoot over to your solids inventory. And the solids inventory is a big issue. And you're doing several different tests with your solids. And you're going to need this to know many different factors. One would be your food to mass ratio. One's going to be how much pounds of solids are under aeration, and another one will be how many pounds of volatile solids are in aeration. And the pounds formula is milligrams per liter times the flow of the plant by MGD. The pounds of the aeration basin is the 8.34, which is the weight of water in pounds, a cubic feet of water in pounds. or excuse me, it's a weight of a pound of water in gallons, 8.34. Then you're also going to need to know the capacity of your tank, your holding tank, in MGD, million gallons per day. Then you're going to need to know the concentration of your total suspended solids or your mixed liquor suspended solids, and that's what's going to give you your solids inventory in pounds. So this is the test that's going to give you the concentration portion of that formula. TSS is total suspended solids. VSS is volatile suspended solids. Volatile suspended solids is the organic content, the actual organisms that are doing the work, your organic content of your solids. It separates the inorganic. So that number is going to be a percentage of what your actual concentration is. And MLSS is mixed liquor suspended solids. That's where your raw wastewater meets with your returned activated sludge. And return activated sludge is anything that's settled in the bottom of a clarifier that comes back into the air bay to help with the treatment, and that is your return activated sludge. Your mixed liquor suspended solids, some people now are calling it biomass, or the last few years, just so it could be a nice term that they could use, but it's mixed liquor suspended solids. It's your organisms. That's your solids. The MLVSS, mixed liquor volatile suspended solids. That's what I was talking about with the organic portion of the biomass. The term fixed and inorganic portion of the biomass is non-volatile, non-biological, with some volatile and biological matter. So it has some, but not all. Organic matter is any chemical substance of carbon source from an animal or vegetable origin. That's what your organic matter means. Inorganic could be substances like sand, silt, eggshells. That's chemical substance of mineral origin, such as sand or gravel. The increase or decrease of MLSS in the process indicates organic loading. So when you're getting more mixed liquor into your system, you're actually adding organic loading, as opposed to if there's a rain event and all of a sudden your plant flow has a whole bunch more flow than you're used to, then that's not necessarily organic matter going into your plant. That could just be rainwater. So that's hydraulic overloading at that point, as opposed to organic loading. Colloidal solids are finely divided solids that are trapped. It gets trapped in your filter. These things don't really settle much in what you call a settleometer test, which is you pour in your mixed liquor suspended solids into a big graduated cylinder or a big beaker, 1,000 mLs, and as it settles out, you're doing readings in 5-minute increments up until a half hour, and then after a half hour, you're going to wait until the end of 60 minutes and get that reading. And some people go back again after that to get another reading to see what it looks like, and that's your settleometer test. Here's another view of the treatment plant. Your solids concentration could be coming from a primary clarifier. Whatever settles down is sludge in a tank, and anything that floats to the top is scum. So your primary treatment could actually have solids to settle to the bottom. Your secondary treatment will definitely have solids to settle to the bottom, and that's where you're going to take samples to do your mixed liquor test. You're going to want to take one from your aeration tank, and then you're also going to want to take one from your plant effluent. And your plant effluent will let you know how well your plant treats. So if you get an influent and an effluent, you can tell what you're started out with and then what's leaving the plant. And the plant effluent is going to be what's on your permit. So your NPDES permit will dictate what you can discharge in an effluent total suspended solids. Here's the apparatuses you're going to need to do this test. You'll need some sort of glass disc filtration media. That's what you see there. Your solids in the treatment process could be as high as 1,000, as low as 1,000, high as 5,000 in an activated sludge plant. Some other types of plants may have a higher range. Your return activated sludge range or your waste activated sludge range. That's the waste activated sludge is the sludge that is no good anymore. It's been in the system too long, so you're going to waste a portion of it out to your digestion process or a holding tank, and then you ship that away to either a landfill. If you dewater it first, then you ship it away to a landfill, or maybe some sort of ag use where you could put it down for a sod farm or something like that. That's where your waste activated sludge will get discharged. And that should be a concentration of about 2,000 to 1,200 in a activated sludge plant. Your biomass has an age, and your sludge age is the length of time the solid stays in the system. So this is why you're taking this test of finding out what your concentration is in the airbag, because you need the concentration to get pounds. Then after you get pounds, you're going to have to find out how long these organisms are in your system by days. So it's going to, each one of these little steps is going to build up to that. And the length of days in your system depends on the design of the plant, the time of year, how your specific plant runs. Some plants run better with higher solids retention times than others. And another way of saying that is MCRT, which is mean cell residence time. So that's another way of calculating days. Your biomass or your sludge will be categorized as young sludge or old sludge. So this is some of the characteristics you'll see in young sludge. You'll see fluffy foam, white foam. Your mixed liquor will be very low. Your color will be light brown. When you're looking at these organisms under a microscope, you'll see shell amoeboids or very primitive type organisms. Their efficiency for consuming oxygen will be a little higher than some of the older sludge, so you'll see high oxygen demand, and then you'll have high microorganism activity. So this is what, when you're doing the plant walkthrough and you're about to take a sample, if you see a lot of these criteria before the sample's even taken, you know, okay, I am dealing with young sludge. You get an idea of what the results should be. But in contrast, old sludge is dark, shiny foam. Mixed liquor is very, very heavy. You see more advanced organisms in the microscopic exams, such as rotifers or water bears, worms even, when you're doing a microscope exam. Have poor consumption of oxygen, and then you'll have less activity because it's older organisms, they're ready to die, and at that point you're going to need to increase your waste activated sludge and your sludge age. Your porcelain funnel, that one is also used with your glass fiber disc, and your porcelain funnel is you see the holes when you do the top view, and that's where you could put that glass fiber disc, which I showed you in this picture back here. You're going to take one of those discs out, and you're going to put it into the porcelain piece, and that's going to filter out your sample under a vacuum. So let me show you that a little bit further. You're going to do a calibration before you even get started on your scale. Make sure your scale is working well and it's calibrated. Sometimes you may need to use a porcelain crucible, and those crucibles They're really good for if you have high solid concentration, you're doing a sample from a digester. You'll need a desiccator where your glass filter membrane pads will end up cooling off and not collecting any kind of additional dust on it to add the weight. You'll need an oven and a muffle furnace. Some muffle furnaces are programmable, and they go up to a very high temperature, and that's going to burn off all the inorganic content and leave you with only the organic content left. Now that's where it's going to give you your MLVSS. You need a wash bottle and some tongs because you're going to be dealing with that oven and that muffle furnace, so you don't want to get your hands in there. You have to stay safe. Got a weighing disc. Sometimes you use a disc instead of using a glass filter membrane. Here's some tips for taking your solids test. So you want to select an appropriate size, sample size for the test. You want to have, if it's a thinner sample, you should have a higher volume of sample versus a thicker sample. So let's say you're doing a sample from a digester, you're going to probably just use maybe a 10, 20 ml sample. But if you're doing one from the final effluent, you may end up having to use 1,000 mLs or 500 mLs because it's far less solids concentration. Your filter pad should be placed in an oven at 130 degrees Celsius for at least an hour for the thinner samples. Then thicker samples will be a little longer in the oven. Pad should be cooled after that for at least 15 minutes and weighed, then placed back in the oven for an additional hour for stabilization. For your volatile samples, then you're going to be adding that cooled pad once you finish weighing it into an oven, and you want to make sure that oven isn't already burning hot. You want it to increase from zero temperature up to the 550, and once it steps up to the 550 now, you're going to keep that burning in there for an hour. Take it out after an hour, let it cool down, and then you're going to weigh it, and then do it one more time for another 15 minutes just to make sure that you're stabilized. Here's your total dry pad weight formula, how to get your solids. Your tire weight is first. That's the weight of the pad before anything else is on it. And then you dry it off the first time in the desiccator, and then you're going to add that weight, and then you do it again, and that's where you get your second weight to make sure that it's that the two numbers, the solids for the first test and the second, are fairly close. Now I'm showing you how to do the test. Here's some pictures of it. I put the glass fiber pad on top of the funnel first, and I sprayed that deionized water on it just to kind of get the pad wet. And I want to seal the bottom of that funnel with the wet pad before I begin the vacuum stage. And this plant particularly had, and I'll show you the pointer, that line over there was attached to an internal vacuum. And there's a little switch that you can hit, an on and off switch, and it'll turn on the vacuum that you can't really see on the counter. But that vacuum will suck out all that the liquid into the bottom portion of that flask, and you kind of see the liquid on the bottom of that flask over here. So that's me looking at my sample, doing a nice meniscus at eye level. I'm going to pour the sample in, and that's what it looks like from the top. So slowly pouring that in. Then I'm going to add the vacuum so I can dry it out, and you keep the vacuum running until you don't see anything else dripping from down here. And at that point, I do a fold, and the folding is just to make sure that the filter doesn't open up and then the solids goes in the oven. or anything that drops into the pad that's going to give me a false reading. So protecting the solids with that. All right, we're going to take another quick break, and we're going to call this a section. So video 2 is done. When we get back, we'll go over documentation. We'll go over some of the safety concerns. Since I'm also a certified occupational safety specialist, I can't do any kind of sampling without telling you about the safety side of samples and sampling in the laboratory. And then we'll also go over at the tail end the new globally harmonized system for classification and labeling of chemicals, because now that's going to change the way you things you see in your plant. So when those chemicals come in, they're going to have new labeling systems, new stickers that are going to show you what the hazards are. The MSDS sheets are gone. There are going to be new SDS sheets. So we'll review that too in the next video. So thank you for this one section. Hang in there. We'll do another one.